to all, I'm Leonardo Mastrototaro, and in this video poster I will present my work in collaboration with Pasquale Serpico, Alessandro Milizzi and Nimetta Saviano on massive sterile neutrinos in the early universe. I will do a general introduction to the problem, then I will talk about the sterile and active neutrino evolution, then I will focus on the temperature evolution, and finally I will present the bounds on the sterile neutrino parameter space. So, in this work we focus on obtaining a precise calculation of the sterile neutrino evolution in the early universe. This is because sterile neutrinos emerge quite naturally in almost all beyond standard model theory, so it's interesting to study their parameter space. Moreover, from BBN and CMB one can obtain some precise calculation on an effective and epsilon p, and we will use these two parameters to constrain the sterile neutrino parameter space. Finally, we will do also a forecast for the future stage 4 ground-based CMB experiment, the so-called CMB S4 experiments. Sterile neutrinos emerge enlarging the Pontecorvo matrix with a 4 mass eigenstates, with a mass higher than active mass. Mass is a free parameter for the model, and the other free parameters are the mixing with active neutrinos. In this work, we have taken sterile neutrinos that mix only with one active neutrino for time. So, as said, we want to obtain a precise calculation of the evolution of the sterile neutrinos in the early universe. To do this, we have to solve the Boltzmann equation, and in the early universe, it's useful to introduce two new variables, x and epsilon variable, linked to the scale factor of the universe and to the momentum of the particle. With these two new variables, the Boltzmann equation depends only on x, on h, that is the Hubble parameter, and on the collisional integral. The collisional integral is a 9-dimensional integral that we reduce to a 3-dimensional integral, and we solve it numerically with the procedure of Hammerstedt. In this way, we have solved it exactly without approximation. We have done the same for active neutrinos, introducing also the time average transition probability from flavors. These are the processes that we take into account for the sterile neutrinos. We have taken a sterile neutrino with a mass under the pion mass, so the main sterile neutrino processes are only with active neutrinos and electrons. A first test for the evolution of sterile neutrinos is to compare our code with the analytical procedure in the reference of Dolgov. In this procedure, the authors have done two approximations. The mass of the electron is put to 0, while the distribution function inside the collisional integral are taken in the Boltzmann limit. We have introduced these two approximations only to do a test in our code, and we found that our results with this approximation are in agreement with Dolgov results, as you can see in the slide. Moreover, we have focused on the temperature evolution. To do this, we have used the energy continuity equation, when ρ is the comoving energy density and P is the comoving pressure. And it's quite useful to introduce a new variable, the Z variable, linked to the temperature and to the scale factor of the universe. There are two main situations for the evolution of temperature: the sterile neutrino decoupling and the decoupling of the active neutrinos. In the table, one can see the temperature at which the sterile neutrinos for some parameters decouple, and we see that these temperatures are always below the QCD phase transition temperature. So we started our simulation below this temperature, the QCD phase transition temperature. We evolved the sterile neutrinos, we found the decoupling. From the decoupling we start to evolve the Z's on the temperature, and at 5 MeV we start to evolve also the active neutrino energy density, and so the active neutrino ρ, to take into account the distortion of the neutrino, of the spectrum of the neutrinos. In the slide one can see some example of the evolution that we have obtained. So, sterile neutrinos impact in the early universe with two parameters. The first of them is the ineffective. N effective in standard model is equal to 3. While introducing stellar neutrino, the definition change, and we can use this definition slide. So N effective at high temperature starts from a value of 4 and then decrease until a stable configuration. There are two main situations for N effective. We have the situation for light mass, where N effective decrease always and then arrive at a stable configuration, and this is due because these stellar neutrino with light mass, almost 30 MeV, are always in equilibrium with the active and electromagnetic plasma, and so they suffer a Boltzmann suppression. While for high mass, and we have done the example of 100 MeV, they decouple early, and so they become non-relativistic. Their energy or their comoving energy increase, and so the N effective increase and then decrease for the decay until a stable configuration. Moreover, stellar neutrinos impact on the early universe on the epsilon p parameter that is linked to the helium-4 mass fraction. To calculate this parameter, we have done a Born estimate calculation. The Born estimated calculation introduced a systematic error that we correct rescaling our results as shown in the slide. Epsilon p parameter is affected by the stellar neutrinos in two ways: by spectral distortion of active neutrino that we have taken into account solving the Boltzmann equation for the active neutrinos, and from changing in the Hubble parameters. So, to obtain bounds from on the stellar neutrino parameter space, we have used the Planck's observation. For the BBN, we have used the epsilon p value of 0.245, while for the CMB, we have used a likelihood analysis that I reported here, and all the bounds that I will present in the next slide are bounds at 2 sigma of confidence level. So these are the bounds that we have obtained in our work. We see that the CMB bounds are stronger for light mass until 30 MeV, while the BBM bounds are stronger for heavier mass. Moreover, in black, we have also plotted the forecast for the CMB S4 experiments. We have used the expected sensitivity for these few experiments, and we found that these bounds are stronger, or will be stronger, than the BBN and CMB. So we expect that in future this new experiment, the CMB S4 experiment, will constrain even more the stellar neutrino parameter space. And here we compare our results with the actual results that one can find in the literature, and here we show that our main improvements are in the CMB sector, as we can see in the figure on the left, but we have obtained an improvement in both CMB and BBN. And so, in conclusion, we have analyzed the phenomenology of a stellar neutrino with a mass under the pion mass, so under 130 MeV in the early universe. We have done a precise calculation of their evolution solving the Boltzmann equation. We have done a precise calculation of their temperature of decoupling, of the temperature evolution, and on the active evolution, always using the Boltzmann equation. Then we have compared the value of epsilon p and N effective at the end of the simulation with the observed value of Planck, and we have constrained in this way the stellar neutrino parameter space. Finally, we have shown also the forecast for this future CMB S4 experiment, and we have shown that this experiment will constrain even more the stellar neutrino parameter space. And here I conclude this video poster. Thanks for the attention.